directions at one point to the gradient is bounded, second derivatives are bounded. How can you get the other direction? So you have all these directions. Let's say it's two-dimensional. You take this direction, twice differentiability, and I claim I can prove that those are bounded. How can you get to this one? Come on guys. It satisfies a Laplacian. The Laplacian is U11 plus U22 is F, is bounded. If, let's say, U11 is already bounded, this is bounded, then of course U22 must be bounded. So you use the PD. You use the Laplacian, and the last piece of the invariance is exactly the normal direction, which is one of them. After, of course, you have rotated. So that's the idea. That was the simple idea. I had other ideas. So that worked out, actually. And you realize sometimes extremely simple ideas can be extremely powerful to prove things. Because if you do that, you cannot apply it. Generally, you do just any direction, you cannot apply it. So you say, okay, this is not of use. But once you remember that you can actually apply it on the tangential direction, and the last direction is coming from the PD, you're done. And that was my contribution, basically. So this was like $100 bill on the ground. Everybody was sort of kicking it. Nobody was seeing it. $100 bill until somebody picked it up and it was $100 bill. Because the proof is so simple and brilliant ideas of the monotonicity formula helps here. It's an extremely strong tool, but you have to use it. You have to see how you have to use it. Okay, let's see how we use it. One line of proof. Of course, that one line now you see it's you have to put it in the setting. Once you do that, that's one line. So psi or z, and now I'm applying to dEu plus and minus here, both of them. That's the product of two of them. This is monotone. It means this is less than or equal to psi at the level 1. For equals to 1 is less than this. But this is just bounded. This is a constant. And it's bounded. Our function has a W22 or W22, we will assume, not the 1, 2, W22, I need to assume. Then that's enough, basically. It's already W2P, so I'm okay with it. So this is a constant bounded. So what happens here? So remember that this is the product of the two functions, phi. R, so let me write R and then dEu plus, and then product of phi R dEu minus. Okay? This is the product of the two of them we have. Now, if I go down here, if I let R go to 0, of course, what we said the first day that the functions are in W2P. If the functions are in W2P, you see that they are differentiable twice almost everywhere. The functions are differentiable almost everywhere. So I will pick up a point which is differentiable twice. If a function is differentiable twice at a point, it means that if you take the mean value of the second derivatives and to let the mean go to 0, gradients go to 0, you will pick up by Lebesgue theory, you will pick up that point's value at that point. So it means that, and then Fatou's lemma, then it means that this is sort of larger than equal to, if we would use Fatou's lemma, larger than equal to phi at 0 plus. U plus and minus. I'm writing in both at the same time. That's the product, so let me write the product. Minus at 0. When I say 0 plus, I mean limits. So 0 plus means R goes to 0. But the functions are differentiable twice. This is just some constant time, some constant 1, or dimension constant times dEu plus at the point, sorry, we have a gradient here. The gradient of this at z, and then the gradient, and then from the other side, but since the function is c2, they both are the same. So I can take this out, I'm going to get power 4, because we have 2 from each side. And there is a constant, Cn. I have to prove this constant is not 0, but the constant is not 0 because if my gradient is not 0, at that point it means there's a flat part, almost a tangential plane, and the pieces are sort of there. The volumes are not getting 0. If it would be something like this, one volume would go to 0, and I get nothing there, I get 0. But since there's a tangent plane, so there are volume on both sides, and this is related to volume on both sides. So what I have here is that gradient of the function, so second derivative, only in certain directions, tangential directions, of the function u at the point z, so tangential, is bounded by constant. That's the, well, the table was longer, it would be one line. So that's the proof of it. And now you complete this with the PDE, and you get the other piece, which tells you that also the normal directions is bounded. Now you realize that you really have a very strong result. This is not related all to obstacle problem. It's a semilinear problem. So it says that for a semilinear problem, if you have monotonicity of the right hand side, then you're going to get the C11 function. Which is not so, which actually, maybe it's not so surprising to people in PD, I don't know. I have no feelings for it. Okay. Now, you might wonder, how do you prove that monotonicity? We have some minutes, I can try to explain that. So you know complex analysis, good or bad? At what level? Okay. All I'm going to use is the function z to power alpha. So f of z equals z to power alpha, and I'm going to take alpha to be different. And you understand that this function is going to be, if you take the real part of this function or the imaginary part of this function, that's going to be r to power alpha sine or cosine. And this function will be, if I'm starting from here, this function will be positive, harmonic function, and positive up to an angle of what is 1 over pi over alpha or something like that. Pi over alpha divided by 2, I don't know. So the angle here, you open it, any angle here, that angle, your function is r to power alpha sine of alpha. It's 0, and then it's positive, and depending on alpha, it will be 0, sooner or later. So let's see how the idea behind the proof is. So the monotonicity formula is saying that this function's h, yes, so we need subharmonicity. So the idea is the following. So let me write it for you again. Is gradient of h plus to power 2. So let me skip this x here and put it here. R to power n. Let me put it here instead. That will be easier to explain. It won't be that accurate, but it will be very simple. And then Rn h minus 1 to power 2. So let me take the origin and the origin. And now I'm saying all the assumptions I had was two functions that are subharmonic, they have different supports, they have disjoint supports. So I can think that if the supports are very nice, like cones, so they separate. But they are not like cones, so you cannot do that. So what you do is actually, the proof goes like, you do a little bit playing with it and then integrate by integration by parts. You take the derivatives with respect to r, and things become a little bit different. And then you do integration by parts. And all integrals are sort of integrals with the gradient are going to the boundary. And you end up with problems of eigenvalue problems on the sphere. So Laplace Beltrami on the sphere. And then you will have two domains pieces, one h plus and what h minus is living. And you will sort of say that the sum of the eigenvalues, not exactly eigenvalues, but combination of these eigenvalues have to be above certain values. These are very tough computations, but people did it, and then successfully they could prove actually this regularity theory. But if your domains are very nice, they are cones, and two-dimensional, you can actually illustrate this, that this is correct. So let's do that. So what we have is a cone like this. So here is h plus is living here, let's say. And then you have h minus is, so h minus is living here. And they are both 0 here. Okay, so this is the support of one of them. This is the support of the other one. Intersection is something like this. They're both 0 here at the origin. So now let's go back again to your z to power alpha 1. So this angle is kind of alpha 1 or something like that. I might not be very exact here because you have to play with this correctly, but maybe I remember it during the course of doing it. And this is the angle for this. So there are two angles. So if you want to take z to power alpha 1 and relate to this, so the imaginary part of this, it will be what? It will be r to power alpha and the sine. The imaginary part is sine, yes? Alpha 1, let's call variable t, theta. If I do this is what I have. The absolute value of z, absolute value, this r is not the same, but it's the absolute value of z to power alpha, and then the sine of this. This function will be 0 here, it will be positive, and then eventually it will be 0, depending on the angle. So the angle I have to choose correctly. They interplay. So this is 0 next time when alpha 1 theta is pi. So alpha 1 theta is pi, it means theta is pi over alpha 1. So this angle is pi over alpha 1. Okay. And this angle is alpha 2 over pi over alpha 2. So the next one is the imaginary of x function. So this is h plus, this is h minus. The imaginary, so plus and minus are not related to positive or negative. So I'm just looking at the function here and then 0. The imaginary of z alpha 2 is something similar with alpha 2. And that's the picture of it. I'm sorry, the board is not so clean, but can't do much about it. So what happens here now is that if I pick this up and put them here, that's the monotonicity formula, it will be like 1 over Rn times the volume of the ball, which is r to power n, approximate. So this is approximate, I'm not being exact. Because the gradient now, the functions are homogeneous and everything I can sort of take out of the integral. It's like Rn times gradient is going to be what? So gradient of h of the polar radius r is going to be, forgetting about that sine thing, sine, cosine, or whatever they are. And then next time I will have something else. I can rotate this and have something here, okay? So I'm considering a rotation of it. It will be r to power what? If I take the derivative, it will be alpha 1 minus 1. So it will be alpha 1 minus 1, and then power 2. That's the first integral. The second one is r 1 over Rn times 1 r to power n, and then r to power 2 alpha 2 minus 1. They cancel, and you get r to power 2 times alpha 1 plus alpha 2 minus 2. Okay, and I claim, if I have computed everything correctly, I claim this is monotone. That's my monotonicity formula in a very simple setting, the most simple setting. And so what these people did, they said that the simple setting actually reflects the general setting. You just have to do the technical part. If you understand it at this level, the other level is the same. But it's very technical to prove it. Here we can prove it, but in 2 lines, basically. I claim this is monotone in R. And it's a question mark. Is that true? So you have to relate this to my pictures. So I give this to you as an exercise to prove it. That if you take 2 cones, and then take the function r to power alpha 1 plus alpha 2 minus 2, that 2 in the front doesn't matter. Okay, is that function monotone when they're related like this, alpha 1 and alpha 2? How do you connect it? Oh, very simple. There is a geometry. The sum of these guys cannot be larger than 2 pi. So the sum is always less than 2 pi. So pi over alpha 1 with the assumption, I'm saying assumption because it is forced assumption, with the assumption that pi over alpha 1 plus pi over alpha 2 is less than or equal to pi. So 1, I can take this out, this is 1, and this is 2. I'm saying that if this is less than 2, this is larger than or equal to 0. That's a calculus, 2-dimensional calculus minimization problem. If that is less than 2, that guy is going to be larger than or equal to 0, the power. If the power is larger than or equal to 0, r to power positive power is monotone. That's the proof of it. Now, with this knowledge, you have to go back and do a proof for the original problem, which is much more complicated than these 3 pages. So this is a completely different way of seeing it. People are still working on this type of problems. It's a very active area of research. To have monotonicity formulas is more complicated for more general problems, and to apply it to different type of problems. If you have other type of PDEs, can you still do that? These are all open questions, and actively people are pursuing it. All right, so with this, I think we will close for today and come back tomorrow. A little more refreshed, everybody. Oh, thanks for your patience. You're exhausted. I'm here. Oh. Because I think it was some misunderstanding because the